In this lesson, we're going to be talking about how to find horizontal and vertical asymptotes. I think this is a really important lesson, not just for the AP Calc class, but for lots of different math classes, and it builds off of the limit skill a little bit that we talked about in the last video. So we're going to start with how we find vertical asymptotes. So it's a good reminder to kind of think about what a vertical asymptote is. So if I have some function, we'll do the function 1 over x. So this is the function 1 over x. And we can see that right here, right when x is 0, this function has a vertical asymptote. If we look at this piece over here in the first quadrant, as x gets really close to 0, these y values are just going to keep climbing and get really close to the y-axis but never quite touch. And the same down here, if we look at the third quadrant, we see that our x values are getting really close to 0, and as that happens, this function keeps going down and gets really close to the y-axis. If I could draw it all the way down, it will keep going forever and get really close to the y-axis but never touch it. So that's what a vertical asymptote is. It's a vertical line that the function gets really close to but never touches. And so how we find that based off the equation is what we do is we look at what x values make the denominator of this equation 0. So if we look at this equation right here, we see that on our denominator we just have x. So if we think about what x values would make the denominator 0, well, it would just be 0, right? If we put 0 in for the denominator, for x, we're going to have 1 over 0. And we know that 1 over 0 is undefined, right? You've been told that can't divide by 0. It's a really bad thing to do. But it really represents this concept of infinity, this concept of a vertical asymptote. And so it's not defined because there is no y value at x equals 0. Our y values keep growing forever and keep going toward positive infinity in the first quadrant and negative infinity in the third quadrant. So we can't say what the output of this function is at 0 because it's not a tangible number. So that's why we get this situation where we have an undefined expression. Another example might be if we had the function 1 over x minus 4. That would be this function shifted to the right 4 units. And so if we had this and we look at the denominator here, we can think about what values of x are going to make this denominator 0. And so if we think, how about 4? If we plug 4 in for x, we're going to have 1 over 4 minus 4, which is going to equal 1 over 0. So the vertical asymptote on this function would be at x equals 4, because it's whatever x value makes the denominator 0. Now, if we're thinking about horizontal asymptotes, we can kind of think about what we talked about with limits in the last video. So if we have some decreasing function, I don't know what it is, but we have some decreasing function, we can see here that this is going to have a horizontal asymptote right at the x-axis. So it's going to have a horizontal asymptote of y equals 0. And so the way that limits are involved is when we talk about horizontal asymptotes, what we're really asking is we're asking about the end behavior of the function. We're thinking, okay, as this function gets really, really big, as it grows, what is going to happen to the y values as x gets really, really big? So if we were to put this into a limit, we could say, as a limit, we'll call this function f of x. So what is the limit of f of x as x approaches infinity? And from our drawing, we can say that that's 0. So really, a limit as x approaches infinity is asking for the end behavior of a function. And if that limit exists, if there is some tangible number, that is going to be the horizontal asymptote of a function. So now let's think about a little bit more complicated. Let's say we have 3x squared plus 6x, and that's all over, let's do 3x plus 4. And this is our g of x. And we want to know what is the horizontal asymptote, if any, of this function. So again, this is like asking what's the end behavior of this function? What's the limit of this function as x gets really, really big? And so when we think about it, if we're thinking about end behavior, we're thinking about x values being really big. So okay, let's look at the top here. If we're thinking about end behavior and we're thinking about x values being really big, between these two terms, this 3x squared and this 6x, if x is really big, which term here on top do we think is going to have more of an impact on the y values of this function? Do we think it'd be the 6x or the 3x squared? And hopefully you'd say the 3x squared, because if x is really big, like 1 million, if we square 1 million, that's going to be way bigger than just multiplying 1 million by 6. So this term right here is called our leading term, because it has the biggest impact out of all the terms in the numerator on this function. And then we can do a similar thing in the bottom. We can say, okay, we have two terms here. As x gets really, really big, which term do we think is going to have a bigger impact on this function? So say x is like 1 million. 3 times 1 million is going to be a whole lot bigger than just the number 4, right? So 3x is going to be our leading term on the bottom. And so the reason why I picked out these leading terms is because when we're thinking horizontal asymptotes, we're thinking end behavior. And end behavior is dictated or determined by the leading terms, because these leading terms have the biggest impact on this function's values. So what we want to do is we want to pick out the leading term on the numerator and denominator. So that's what I did. So I decided the leading term on top was 3x squared, and the leading term on bottom was 3x. Now, I'm not saying that this function is the exact same as this function. I'm just saying that if we're thinking about end behavior, these are the only terms that I really care about, because these are the terms that are going to determine end behavior. Okay, and so as you may have noticed, we can simplify this term a little bit. 3x squared over 3x. Well, those 3's cancel, and one of those x's will cancel, so that should just leave us with x. So this means that if we look at the end behavior of our original function we started with, as x gets really big, this function is going to end up looking like the line y equals x. If we were to take this function, like throw it in Desmos or something, and zoom way out, then it's going to, from a distance, zoomed way out, look like just the line y equals x. And we all know what that looks like. That's just a line, bad line, that's just a line that goes through the origin. And so as this function gets really, really big, as x gets really big, the line y equals x just keeps going. It keeps going up forever, and there's no limit to it. So this function actually has no limit. It's going to keep growing to infinity. So that means that this function here is also going to keep growing to infinity as x gets really big. So this function actually has no limit as x goes to infinity, or another way to say it is it has no horizontal asymptote. It has no limiting value. And we decided that by analyzing these leading terms out here. So let's look at another example. Let's say that we have g of x equals 3x plus 4 over 4x squared plus 7x. Sure. Okay. And so now we want to figure out what the horizontal asymptote of this function is. So again, we're thinking end behavior. We're thinking as x gets really, really big, what happens to this? And so again, we want to follow that method of analyzing the leading terms on top and bottom, because those are going to have the biggest impact on the end behavior of this function. So if we look at the top here, as x gets really big, which one is going to have a bigger impact, this 3x term or this 4? And so obviously this 3x is going to get bigger much quicker than that 4 will, because that 4 is just a constant, it's not going to change. So that's going to be our leading term on top. And then down here on the bottom, which one's going to have a bigger impact, 4x squared or 7x? And it's going to be that x squared term, because squaring something makes it a lot bigger than multiplying it by 7. So our leading term is 4x squared. And so we can do a bit of simplification here. One of these x's is going to cancel, so we're left with 3 over 4x. So this, again, this function is not equal to this function, but if we're thinking about the end behavior, this function's end behavior is going to have the same as this function's end behavior. Okay, so 3 over 4x, what does that tell us? What does it tell us about horizontal asymptotes? Well, hopefully, if you were to throw 3 over 4x into Desmos, you should get something that looks generally like this. So it's 3 over 4x is the function 1 over x dilated a little bit. So it's going to generally look something like that. So if we look at this function and we look as its end behavior as x gets really, really big, or as x goes in the negative direction, gets really, really small, we see that in both quadrants this function approaches 0, right? It has a horizontal asymptote right at the x-axis. So, and in both directions. So this function, the limit of this function as x approaches infinity, or this function's horizontal asymptote, is equal to 0. And more specifically, the line y equals 0. So this is going to be the horizontal asymptote of that function. Last situation that we could encounter is, let's say g of x was 4x squared plus 6x plus 5, and that was all over 2x squared plus 3x plus 4. And we want to know horizontal asymptotes and behavior. So okay, again, we want to look at the leading term on top and bottom. So our leading term on top is going to be this one, and our leading term on bottom is going to be that one. So we can write that as 4x squared over 2x squared. And again, you might see some nice simplification happening. These are just going to cancel, and then 4 divided by 2 is 2. So what does that tell us? Well, let's look. What does the graph of y equals 2 look like? Well, that's just a horizontal line right at 2. So that means that this function has a horizontal asymptote at y equals 2. So the end behavior is that this function is going to get really close to the line y equals 2. And we decided that by looking at these leading terms. So those are kind of the three situations when we're finding horizontal asymptotes that you might have. One is you could have this situation where the leading term on top and on bottom have the same power, so they cancel and we're just left with a nice number like 2. Or we could have this situation where the leading power on bottom was bigger than the leading power on top, and that's when we got a horizontal asymptote of 0. Or the last situation is we could have the leading term on top be the bigger one, and the leading term on bottom be smaller, and that's when you're going to get a limit or horizontal asymptote that doesn't exist. No limit or / horizontal asymptote. So those are the three situations, and it really all comes down to what's the relationship between the leading powers in the numerator and denominator. So hopefully this gives you a good starting idea of how to go about finding vertical and horizontal asymptotes. As always, if there's anything else you'd like to see or any kinds of problems or topics mentioned, please let me know in the comments and give it a subscribe.